Ever looked at a modern circuit schematic and felt like you were drowning in an alphabet soup? JFETs, MOSFETs, LDMOFETs, IGBTs, the sheer volume of advanced semiconductor acronyms is enough to make anyone's head spin. But today, we're going to decode them. In this explainer, we'll look at the very specific engineering problems that force the invention of each of these devices, and see exactly how their physical structures serve as the ultimate solutions. By the end, these won't just be random letters to you. They'll be distinct, brilliant tools in your engineering toolkit. Here is our roadmap so you can easily file these away as we go. First, we'll meet the MOSFET. Second, we'll look at power and precision. Third, characteristics and safety. Fourth, biasing methods. And finally, the ultimate hybrid, the IGBT. All right, part 1, meet the MOSFET, our insulated hero. Okay, let's dive into this. To really appreciate the MOSFET, you first have to understand the classic JFET's biggest weakness. The JFET is a great device, but it has a fundamental limitation. If its gate slips into forward bias, your input resistance drops like an absolute rock. Engineers needed a foolproof way to prevent gate current, no matter what voltage polarity was applied. Enter the MOSFET. By physically separating the gate from the channel with a microscopic insulating layer of silicon dioxide, they created a device with nearly infinite input resistance. Now, there are two main flavors here. First is the Enhancement-mode, or E-MOSFET. Notice that its substrate extends completely to the insulator. There is zero structural channel connecting the drain and source. Think of it like a parallel plate capacitor. The gate is one plate, the channel area is the other, and the silicon dioxide is the dielectric. Applying a positive charge to the gate pulls negative electrons into that region, literally inducing a channel out of nowhere. Then you have the Depletion-MOSFET, or D-MOSFET. This one actually has a physical built-in channel from the factory. A negative gate voltage pushes electrons away, depleting the channel, while a positive voltage attracts more electrons, enhancing it. Moving on to part 2, power and precision. It's time to muscle up. As brilliant as the standard lateral MOSFET is, it had a problem. Its long, thin channel created high electrical resistance, which wasted power as heat. That severely limited early E-MOSFETs to low-power applications. To fix this, engineers completely reimagined the physical geometry, building 3 heavy-duty descendants. First up, the LDM-MOSFET, which dramatically shortens the lateral channel to allow for much higher current and voltage. But what if lateral space is limited on your silicone? Well, you go vertical. The V-MOSFET cuts a V-groove structure straight down into the silicone, creating a shorter, wider, vertical channel that handles massive power dissipation and even improves frequency response. And then we have the T-MOSFET, which also uses a vertical channel but in a T-shape. This optimizes the surface area even further to achieve an incredible packing density while keeping resistance remarkably low. Let's think about how the LDM-MOSFET actually pulls this off in practice. When you visualize the path of the current flowing through it, you'll find a very short N channel induced in the P layer between heavily doped source and drain regions. They achieve this through tightly controlled diffusion, and it all comes down to a simple rule of physics. A shorter channel equates to lower resistance. Less resistance means less heat generated, which ultimately means this device can handle significantly higher voltage and current than its conventional counterpart. Now, brute power isn't the only challenge in electronics. Speed and frequency are just as critical. Standard FETs suffer from high input capacitance because of that gate structure we just talked about, heavily restricting their use at higher radio frequencies. The solution? The dual-gate MOSFET. By literally dropping a second gate in series, the overall input capacitance is drastically slashed. This makes it an absolute powerhouse for high-frequency RF amplifiers. Plus, that second gate gives engineers a dedicated input for automatic gain control, meaning they can dynamically adjust the amplifier's response on the fly. A real game changer. Part 3, characteristics and handling. Let's look at the mathematical quirks of these devices, and more importantly, the very real dangers of working with them. So, the absolutely crucial point here is understanding how these different devices wake up and turn on. Both types of MOSFETs are what we call square law devices, meaning their transfer curves are parabolic. But their equations tell 2 very different stories. The D-MOSFET, because it has that physical channel, acts a lot like a JFET. It conducts fully at 0 volts and requires a negative cutoff voltage to shut down. But the E-MOSFET has no physical channel, remember? Its curve starts way further down the axis at a specific non-zero threshold voltage. Until your gate voltage exceeds that specific threshold, the E-MOSFET is essentially a brick. It conducts 0 current. Now, listen closely, because handling these components in the lab is quite literally a matter of component life and death. The MOSFET's greatest superpower, its insulated gate providing nearly infinite input resistance, is exactly what makes it so vulnerable. Because that resistance is so high, static electricity has absolutely nowhere to go. A tiny, imperceptible static charge from your finger can easily puncture that microscopic layer of silicon dioxide, instantly ruining the device. You have to keep them shipped and stored in conductive foam. You must ground your soldering iron in assemblies. You never plug or unplug them with the power on, and you absolutely never apply an input signal if the main DC power is off. Treat them like unexploded ordnance, because one wrong move with static, and they are toast. Part 4. MOSFET biasing methods. Let's set the stage. To actually put a MOSFET to work in an amplifier circuit, you have to establish biasing. This is basically a DC foundation that sits the transistor at the perfect resting point, the Q point, ready to amplify an incoming AC signal without clipping or distorting it. Let's look at the E-MOSFET first. Because it absolutely requires a gate voltage that exceeds its threshold just to wake up, setting the gate to 0 volts is impossible here. It wouldn't do anything. Instead, engineers use clever methods like voltage divider or drain feedback configurations. Both of these methods steal a little fraction of the main supply voltage and feed it directly back to the gate. This guarantees the gate is sitting firmly at a positive voltage, keeping that induced channel wide open and ready for action. And this brilliantly illustrates why the D-MOSFET is such a remarkably versatile component. Remember, the D-MOSFET has a built-in channel, meaning it inherently conducts at 0 volts. Because it can seamlessly handle both positive and negative gate voltages, operating in either enhancement or depletion modes, we can use a beautifully simple zero-bias setup. You literally just tie the gate to ground through a resistor. The gate sits happily at exactly 0 volts. When an AC signal arrives, it smoothly swings the gate voltage into the positive and negative ranges, perfectly modulating the current without needing any of those complex DC voltage dividers. It's elegant and highly effective. Finally, Part 5, enter the IGBT, the ultimate hybrid. Up until now, we've watched engineers incrementally improve these devices. But sometimes, incremental isn't enough. You need a revolution. See, bipolar junction transistors, or BJTs, can handle massive currents, but they require annoying, power-hungry input currents just to drive them. MOSFETs, on the other hand, have brilliant zero-current inputs, but struggle with high-voltage saturation. The solution is essentially a Frankenstein's monster of a component, the Insulated Gate Bipolar Transistor. The definition really says it all. It's a voltage-controlled device combining MOSFET input characteristics with BJT output conduction. It takes the heavy-lifting, low-saturation voltage capability of a traditional bipolar transistor and bolts it directly onto the zero-current, voltage-controlled insulated gate of a MOSFET. It doesn't load down your driving source at all, but it can switch absolutely massive loads on the output. When you put these components head-to-head, it is fascinating. This is the ultimate showdown table. Just look at the inputs. The IGBT matches the MOSFET perfectly with high input resistance and voltage drive, entirely crushing the BJT. But then look at the output saturation voltage. The IGBT matches the low voltage of the BJT, totally beating the MOSFET. Now sure, the pure MOSFET is still the absolute king of high-speed nanosecond switching, but for anything else, the IGBT is the undisputed superior choice for high-voltage switching, specifically anything over 200 volts. It is the ultimate compromise device. But just like Frankenstein's monster, the IGBT has a dark side. Because of the incredibly complex layering of semiconductor materials required to build it, it accidentally forms a hidden, parasitic transistor right inside its own structure. Under normal conditions, this ghost component just sleeps, it does nothing. But if you push the IGBT too hard and exceed its maximum collector current, that parasitic transistor wakes up. It feeds back on itself in a fatal condition known as latch-up. The device locks permanently into the on position, ignoring your gate commands entirely, which usually leads to catastrophic circuit failure. It's an incredible tool, but you have to respect its limits. So let's take all this textbook theory and put it straight into the real world. Imagine you're the lead engineer designing the motor controller for a modern electric vehicle. You've got a 400-volt battery pack delivering massive torque to the wheels, and you need to switch that power thousands of times a second. What do? Do you choose the ultra-fast switching speeds of the standard MOSFET, knowing it might really struggle with high-voltage saturation? Or do you reach for the heavy-duty hybrid IGBT, accepting slightly slower switching for that 400-volt dominance, while carefully engineering your way around the risk of latch-up? That isn't just a hypothetical. That is the exact engineering decision happening in automotive labs right this second. So what would you choose? Think about it. And let that spark your curiosity for your next deep dive into electronics. Thanks for joining me on this explainer, and I'll catch you next time.